Oh, thank you. All right. So last material from chapter 3, and therefore the last material that could be on the so-called midterm, which is really good job. Okay. What we're going to look at here is when you obtain an approximate solution to AX equals B, which is what you would get from the method that we've seen, like Gaussian elimination, because when a computer's doing work, there is going to be some rounding error of some kind. We want to try to get a handle on how big that error could be. So, because we're dealing with magnitude, we need to be able to discuss magnitude for vectors and matrices. We're doing matrix A times vector X equals vector B. And that leads us to norms. Now, you've already seen in our classes the concept of magnitude, for vectors at least. The Euclidean length of a vector, the square of the sum of squares of its components. And it is one of the notions of magnitude that we'll be seeing here. But there are other ones too that can be more convenient to work with. So, and also, what if it's a matrix, not a vector? How do you measure the size of that? So that's what we'll take a look at that too. Okay. So first, vector norms. So this is one that I mentioned, the one that would be familiar to you. And this is expressed differently in different books. Some just use the absolute value symbol because you can think of this as a generalization of absolute value to vectors. I personally prefer using the double bar to convey magnitude, especially when there are different notions of magnitude. So when is a function of a vector that maps a vector to a real number an appropriate notion of magnitude? So we have these conditions to define that. So a function that maps a vector to real numbers is called a norm if it satisfies these conditions. So first of all, because it's magnitude, it should definitely not be a negative number. And the only time that it should be 0 is if a vector you're taking a norm or magnitude of is itself 0. Also, if you scale a vector, then that should scale the norm by the absolute value of the scaling factor. And then also triangle inequality needs to be satisfied. Okay. So here are some examples of vector norms. There's actually a whole family of them called P norms, also referred to in some books as LP norms. It corresponds to a space of vectors defined to be LP, for which this norm is finite. So what we have here for a P norm is a natural generalization of the Euclidean length or magnitude that you're familiar with from calculus. So the P norm is where you take the sum of all the components of the vector in absolute value raised to a p power, but then the sum is raised to the 1 over p power. Now, we can define this for whatever p we like, but there's only certain values of p that are of general interest. For example, the 1 norm, that's just the sum of the absolute values. And then the 2 norm, this is one you're most familiar with, so square sum of squares, all the components. But I want to point out, it can also be written this way, square root of x Hermitian transpose times x, where the Hermitian transpose is transpose and complex conjugate. So that way this formula works for real or complex vectors. And this corresponds to just a generic dot product that you would deal with in calculus. And finally, if you let p go to infinity, what happens is the larger P is, the more the largest component contributes to the norm. So if you take that to its extreme and P goes to infinity, the largest component is the only one that matters. So it's just the absolute value of the largest component. And we have this relationship that the P norms satisfy, that the larger P is, the smaller the norm gets. Because you have, as P increases, you have less and less of a contribution from components other than the largest one. But we do have an equivalence among all of them, that for any two P norms, so the P norm and a Q norm, that are all defined in this manner for appropriate P and Q, you can always find constants C1 and C2 that are independent of X, so that the P norm is bounded above and below by these constants times the Q norm. So what that means is, suppose you have a sequence of vectors, and you want to know if it's converging to a limit. And then you determine that it actually is converging to a limit by in some P norm. But because of norm equivalence, if it converges in one norm, it converges in all of them. The convergence may happen at somewhat different rates, but it does converge. So you can't have a situation where the sequence of vectors is converging to 0 in one norm and it doesn't converge to 0 in another, because of this relationship right here. But however equivalent, certainly some norms are more convenient than others for different situations. So here's how we define convergence in terms of a norm. So if you have this situation where the norm of a difference goes to 0, so now we're talking about the limit of a sequence of numbers, not of vectors, because you're taking the norm. If that sequence of norms converges to 0, then the sequence of vectors xk converges to x. Now, I should point out that if we do have convergence based on this definition, because the norm of a vector is 0, if and only if the vector you're taking the norm of is 0, that means that each component of xk is converging to the corresponding components of x. So convergence norm-wise implies convergence component-wise too. For special case of a 2 norm, we have this inequality that's quite convenient for proving a lot of things, the Cauchy-Schwarz inequality. You may have seen this in calculus. So the absolute value of the dot product is less or equal to the product of the norms. The general is equal to the product of the norms times the cosine of the angle between them. So considering cosine bounded by 1, then we get this. Now I'll show you a proof. Just for fun. So if I take this expression here, the norm, 2 norm, squared, x minus cy, where c is some constant. Now for convenience, we're going to assume that everything is real. And this is an important property to keep in mind. If I have the 2 norm squared of a difference of vectors, so by definition, it's the vector of Hermitian transpose times itself. But then you can expand this, and this is what you get. So just foiling it out. But keep in mind, for even real vectors, the dot product is commutative, but for complex vectors, it's not. You have a conjugate to take into account. But in the case of real vectors, you are allowed to combine these terms. So what we see is that this norm is a quadratic in the constant c. So we can set this equal to 0 and find the roots. So those are roots. thing is, this is equal to the norm of a vector squared, which must be non-negative. So, so this quadratic has to either be entirely above the x-axis, or it could touch it, but it can't cross it into negative territory. So the only way that this is valid is if we need this expression. So this expression could not be positive. So it must be, so this has to be less than or equal to 0. So in the case of a complex root or a double real root. So if you say that this is less than or equal to 0, Cauchy's force inequality falls right out. So, questions about how this was proved? Okay, so that's vector norms. So we're going to build on vector norms to find matrix norms. Now this is a rather strange definition. If you have a vector norm, such as a p norm, it induces a matrix norm. So the p norm of a matrix A is defined as the supremum. The supremum is the least upper bound. So, sorry for real analysis flashback there. Overall non-zero vectors of the vector norm of A times X divided by the vector norm of X. Or it can be equivalently defined as the maximum over all unit vectors in that norm of just A times X. So you can think of it as the maximum extent to which multiplying by A amplifies the magnitude of a vector that A is being applied to. Okay, can anyone tell me, why is it that it's okay to use maximum here, but not here? Here we have to use supremum. Anyone tell me the distinction?
The maximum has to be inside the set that you're dealing with, and the supremum doesn't.
Yeah, another way of putting it is this set of unit vectors is compact, while this is not. So, yeah. And the continuous function on a compact set has a maximum and minimum. But yeah, the supremum might fall outside the set of all these values for non-zero x. Okay. Now, here are some matrix norms corresponding to the vector norms I mentioned earlier. So the one norm, so the vector one norm is the sum of the absolute values of the components. The matrix one norm is where you go to each column, you add up the absolute values of all the entries in that column, and then out of all those column sums, you take the largest one. And I have a proof of that worked out. Okay. So what I'm doing here is I'm assuming that x is a unit vector in the one norm sense. So it's one norm is equal to 1, those absolute values, the components all sum to 1. So then I want to see how large can this get. I want to find its maximum under this assumption on x. So, okay, so I'm writing out what it is. So the sum of all the absolute values of the components of AX. But then I express AX this way using the definition of the matrix vector product. All right, then triangle inequality, and now I have this rearranged. Now, notice what I have here, though. This is the sum of the absolute values of all the entries in column J. So I can replace this column sum by the maximum column sum. And now, this part right here is independent of J, so I can factor it outside of this summation. So now I have a maximum column sum times the sum of all the absolute values of the components of X. But X is assumed to be a unit vector in a one-norm sense. So this sum that I've highlighted here is equal to 1. So we're left with this. So now we know that norm of AX, one norm of AX, is less than or equal to this. But that's not the whole thing. We need to show that there's a specific vector, X, for which this inequality is actually an equality. And that's not hard to do in this case. If I choose X to be a vector that's a capital J column of identity, so it's all zeros except for 1 in a capital J position, where capital J is where the maximum column sum occurs. So in that case, I use that vector X in here, and so this expression turns out to be equal to this. So equality has been achieved, therefore, this is, so this value is the maximum of A times X over all unit vectors X. So therefore that is the matrix 1 norm, is this maximum column sum. Questions about what happened here? Similarly, the infinity norm is the maximum row sum. So you consider each row of A, sum the absolute values of all entries in that row, take a maximum of those sums, that's the infinity norm. The way you would prove it is very similar to what I just showed you for a case of the 1 norm. The 2 norm is more complicated. I won't get into details here, but it's the square root of the largest eigenvalue of A Hermitian transpose A, which is also known as the largest singular value of A. I haven't talked about the singular value decomposition in this class. I think it might be something I'll bring up later. But the big point I want to make here is, whereas these matrix norms can be computed in order n squared time, where if it's an n by n matrix, this takes order n cubed time in general case. Also, it requires an iterative method to really what you're doing is just approximating this. Now, there is a norm function in MATLAB, and by default, the norm function will use the 2 norm for whatever matrix or vector you give it. So that can actually be pretty expensive. So when you're computing a matrix norm, you might want to specify, using a second argument, computing a different norm, like a 1 norm or an infinity norm. That'd be more efficient. Here's another matrix norm that is not induced by a corresponding, oops, I should say vector norm, a Frobenius norm. So if you take your matrix and reshape it into a vector and take the two norm of that vector, so square root of sum of squares of all the components, that is a Frobenius norm. So at least this one can also be computed efficiently. Now, so matrix norms are all equivalent, just like vector norms are. So now I can discuss sensitivity of a problem AX equals B. So last semester's class, in 465-60, I talked about in chapter 2 the condition number. So the condition number is how much backward error or error in the input is amplified to obtain error in the output, forward error, which is the error we really care about. So when the condition number is large, it means that the problem is very sensitive to changes in the input data. Now, last semester for a general problem, we had to give our vague definition of condition number, and for simple cases like you're just computing y equals f of x, it was possible then to define a condition number in terms of a derivative. But for more complicated algorithms, it's very difficult to do. But in the case of solving AX equals B, I can give you a formula for a condition number. Now, what I mentioned, this came up last semester, that so the practical solution of AX equals B is the exact solution of a nearby problem. So here I define a nearby problem to be solving a system of linear equations where the matrix is perturbed. Now I should mention that in this corresponding discussion in the text, I make it a little more general that we have a nearby system where both the matrix and the right-hand side are perturbed. But for just introducing you guys to the concept of condition number, I'm going to simplify matters and only assume that the matrix is perturbed. So in the case of epsilon equals 0, we have the exact solution of AX equals B. So, but if we do have a perturbation here, so we're solving a perturbed system, then how much does that change the solution? How much does a change in the system impact the solution? Well, we'll try to get a handle on that. That gives us a notion of sensitivity of AX equals B. So here's what I do. Actually, I'm going to put this onto a new page. Oops. Okay. So what I can do here is I can rearrange this equation to get an expression for x of epsilon. And that's what I have here. I won't get into this because there's actually a homework problem that's related to this. So now I have this minus x over a norm of x. Here we're looking at relative error. So I'm dividing by the norm of x, the exact solution. Now, x is the exact solution, so x is equal to A inverse B. So A inverse B and x will cancel, and this is what I have. Now to get a handle on this, okay. I have at the matrix norms have this property called the submultiplicative property, where the norm of a product is less or equal to a product of norms. So I can use this to say this is less or equal to norm of A inverse times norm of capital E times norm of x of epsilon, and I factored out the epsilon, and I put that here. And then I'm multiplying and dividing by the norm of A. And the reason for that is, something is up here. Okay. Sorry, I'm cheating a little bit. Oh, okay. I'll do that later. So here I have norm of A times norm of X down below. And I can actually all right, hold on a second. It's been a couple of years since I've looked at these notes. Oh, okay. So I can say that, I think I'll just leave it like this. So what I have here is norm of E over norm of A is the relative change in the problem, because capital E is a perturbation of A. So this fraction right here is a measure of how much a problem has changed. For small epsilon, this ratio is going to be approximately 1. And certainly it converges to 1 as epsilon goes to 0. And then we have this factor here. So by including this A down here in terms of measuring the change, relative change in the problem, I have this factor left, norm of A times norm of A inverse. So I define that to be the condition number of A. So what this is saying is that the relative change in the solution is roughly bounded above by the relative change in the problem. And sorry, I goofed earlier, right? Which is a epsilon capital E over A. That's the relative change in the problem. Is amplified by this number, the condition number, norm of A times norm of A inverse. So if a problem changes by a tiny bit, Ax equals B, the solution could conceivably change by a factor of this much. So if this value is large, we say the problem is ill conditioned. If a condition number is at least 1, so for example, suppose A is identity, then kappa of A, condition number of A is 1. So that would be an example of a matrix that is perfectly conditioned. Another way of thinking about it is, if a matrix is ill-conditioned, that means it is close to a singular matrix. So in other words, a small perturbation of A would give you a matrix that is singular in the ill-conditioned case. And this is a better measure of better measure of near singularity than the determinant. Because even you get a situation where a matrix is not really close to singular, but again, a very small determinant, give the impression that it is nearly singular. Or you could have a matrix that is nearly singular based on the condition number, but its determinant is large. So if you want to matrix nearly singular, use a condition number, not the determinant. To get the condition number of a matrix, Cond of A will, by default, give you a condition number in the 2 norm. So again, the 2 norm is the default. Or you can specify a different norm using a second argument. So for instance, a 1 norm, or you say, you set P equal to inf, INF, if you want to use the infinity norm. Or FRO, FRO, for Wiener's norm. So questions about the derivation of the condition number? I have an example from a text about the condition number. It's from chapter 2. Oh, it's here somewhere. Okay, we'll go to the previous section. Okay. Okay, I'm gonna have to go back and type this in. Oops. All right. Let me copy paste. Oh, okay. Okay, now, first I want to take a look at the norm of the difference between these 2 vectors. Oh, I'm in format rational here at once. Format short. Okay, so B2 is a 1% perturbation of B1. So I'm going to solve X equals B with these 2 right-hand sides. So first is B1. Okay? So keep in mind that the right-hand side is now changed by 1%. This should change by a bit more than 1%. Now let's look at the condition number of A. Pretty bad. So actually, if I look at oh, I do. We got to call this X2. Okay, so here's amplified by quite a bit. And basic condition number, that's 30,000. Well, actually, if I look at this relative difference divided by the relative difference in the right-hand sides, okay, and I compare that to the condition number of A, it's almost as much. So, so whatever condition number is how much the solution can change in terms relative to change in problem input. So here we got fairly close to that theoretical maximum. Now, I will admit that this example was contrived to bring out a bad case, because for certain other cases it might not be so bad. But that's just it. You don't know. So you have to take that into account. Okay. The singular values of A I look at those, well, this is 2 by 2, 2 by 2 matrix. So we have, so first one nearly 1, second one's quite small. The condition number is actually the ratio. And I should mention the condition number is defined differently based on what norm you choose. So the condition number is P norm of A times P norm of A inverse for whatever P you choose. And each P will give you a different value. The condition number in the 2 norm is equal to the ratio of the largest singular value to the smallest. So imagine this ratio be pretty large. So even a very tiny matrix can be ill-conditioned. So it turns out that each row of this matrix, so the first row is nearly a scalar multiple of the second row. And that's what happens when you have a singular, or nearly singular 2 by 2 matrix. Any questions about this example? A small singular value, you take it as a measure of distance between this matrix and the nearest singular matrix. In other words, you could perturb A by some matrix of this magnitude and get a matrix that's singular. So it's very close to the set of singular matrices. In which case AX equals B could not be solved at all. All right, one thing I want to mention is a process called Iterative Refinement. This brings to mind this very important concept of the residual. So if you were trying to solve AX equals B and you get an approximate solution X hat, then you think in terms of substituting into the system. B minus AX hat, which you want to be 0, but since X hat's only an approximate solution, you're going to get something non-zero, and that's the residual R. So if a residual is small, you might think, oh, I have a pretty good approximation to the exact solution. Well, you have to be careful about that. So if I define the error, this is what we really want to be small. The exact solution minus the approximate. So now I can use this to obtain a relationship between the error, which is what we want, but we can't get, and the residual is not what we want, but we can get it. So now we have A times the error. Well, if I replace E by its definition, X minus X hat, so then I have AX minus AX hat. But X is the exact solution, so AX is B. So now I have B minus AX hat, but that's just a residual. So in other words, A times the error is residual. So now if I want the relative error, and that's norm of E divided by norm of X, well, E is A inverse times R, and then I multiplied and divided by norm of A. So now what I have here is this is less than or equal to norm of A times norm of A inverse times norm of R. That exposes a condition number. And then 1 over the norm of A times norm of X is less than or equal to norm of B. So I'm using this relationship to get from AX, norm of A, norm of X here to norm of B down here. Because these are in the denominator. Why I can get away with that. So what we have here is the relative norm of the residual, so norm of R divided by norm of B, is amplified by the condition number to get an estimate of the relative error. So this tells you that just because you have a small residual relative to norm of B does not mean that you have small relative error. You have, not if the matrix is still conditioned. So beware of that. So you could have a small residual and still have a large error. Now this relationship between the residual and the error can be used to develop an iterative process for solving AX equals B, called iterative refinement. So the idea is to use this relationship, because the residual is something that's known. So you use this relationship between the error and residual to estimate the error. You solve this system, just like you were solving AX equals B in the first place. Then you rearrange this relationship, and the exact solution is the approximate plus the error. You have an estimate of the error, so you can put that in here, and you update your solution. Now you have what is hopefully a better approximation. So now you can repeat this process. Take your residual, estimate the error, update the solution. You just keep going. I'm going to show you the algorithm. Okay, here it is. So initially our approximate solution is 0. Our residual is just b minus ax, which in this case will just be b. So that's our starting point. So now you carry out this iteration. You use a residual to estimate the error. Add the error onto your previous solution to get your new solution. Then for your new solution, you update your residual so that you can use that in the next iteration to get the error again. And you just keep going until you have detected convergence. Any questions about the algorithm? One thing I want to point out about the algorithm is this. I've copied the last line of the algorithm where the new residual is computed. Now this is at odds with the definition of residual. Residual is b minus ax. So why is it computed this way rather than this way? And the reason why is cancellation error. So, because you can show that these two are equivalent by expressing xk plus 1 in terms of xk, because xk plus 1 is equal to xk plus an error estimate. So you can use that to extract the previous residual rk, and then this is what's left. So the reason why this one is a better idea than this one is keeping in mind the convergence. So xk is supposed to be converging to the exact solution x. Therefore, the error should be going to 0. Residual also should be going to 0. In other words, both of these vectors are going to 0. This vector is also going to 0. On the other hand, b is a fixed vector, not going to 0. X, k plus 1, that's your approximate solution. That's supposed to be converging to the exact solution. So a times x, also not converging to 0. So in other words, what's happening is you're taking two vectors that are not going to 0, and you're subtracting them to get something that is going to 0. That's cancellation error, where the difference is much smaller than the entities that you're subtracting. So here, even though this is meant to be smaller than either one of these are still also, these are small themselves. So you're reducing a cancellation error by obtaining something that's nearly 0 by subtracting two other things that are also nearly 0. So this is a much more numerically stable way of updating residual than using the definition. So there's little things like that that need to be taken into account when designing numerical algorithms, because there's so many places where round-off error can get you. All right. questions about any of this, or about homework for that matter. It's a good amount of time. Everything's going swimmingly for homework?
I won't go that far, but.
Okay. I appreciate your honesty.
Yeah, there's a couple on homework 3 that I've been struggling with, but it's just getting everything in the right order. Like what you were talking about earlier, with the 342, that showed that the forward absolute error is given by. That's just. I keep going in circles with everything I do.
Oh, I see.
So
Yeah.
I decided to give up on it until I finish all the other ones, and then I'll come back.
Okay. I'll simply say it's not a very long thing.
Oh, I've made it very long.
Okay. Yeah. So you need to regroup on that one.
Okay. Yeah, and the only other problem that I've been working on for a while was the 333, which is just the bandit stuff, getting the right number of operations that are used and the indices, but I've just been doing trial and error trying to get it to work right.
Oh, I see.
Yeah, because I actually finished the whole problem, and then when I went back to check it, I realized that I've ignored half the directions. So I'll start over.
Okay.
Yeah.
Um,
But mainly B, this is taking me a while. I just finished the code to deal with the upper and lower bandwidth. I just need to perform Gaussian elimination on it.
Okay. Yeah, the thing that's a pain about banded LU is the exceptional cases. Like, okay, you know how many entries you need to eliminate in a column, you know how many, for a prior problem, you know how many entries need to be updated when from a row operation, but what if, for one case or the other, you go off the edge. So in that case, it's convenient to use like the MATLAB's max and min functions to take it into account.
Yeah, I figured that out this morning.
Okay.
Yeah, because I kept having a index issue where
Yeah.
it worked until I got to the main diagonal, and then I would be running over on the next step.
Yeah.
So I did the max. I think it was something like n minus p minus 1 or something like that, and it took care of that problem.
Yeah, because things when you get an error, it's easy to think, oh, what you're doing was totally wrong. I think, well, no, maybe it wasn't totally wrong; it's wrong in that one case. And then students end up fixing something else that didn't need to be fixed. So
Yeah, I just ended up making it print every matrix, like every time.
yes, yeah, that's what you got to do. Apparently that's sacrilege on my part to say that, because there's some people who believe very strongly in debuggers.
Print statements. Print statements,
yeah.
Display statements. That's not good too.
And funny thing is when I've seen post by, who was at the time the chair of the computer science department at Stanford. They I just use print statements. It's like, okay, I'm a pretty good company. I've built it a long time. Okay. Now we talked about certain problems. Are we sure that no one else has any questions? What I cover on Wednesday will be from chapter 5. Won't be on this midterm, but there'll be homework on it later. This homework, if you look at the schedule, not due for a while. That's just because of the midterm, but I'd recommend at least taking a look at these, doing as much as you can, that might help you. This is, well, especially the non-MATLAB ones. There aren't MATLAB problems from the midterm. Whereas the final is all MATLAB stuff. Well, if you choose that option. I probably should have shut down Teams.
It's not a dumb question, Michelle.
Yeah. So this is not a good time to send me a message. I won't tell her that this will be immortalized on YouTube. Okay. Well, I guess we're good then. Of course, anyone can ask questions after I stop recording, which will be